All right, here's what it says. An industrial consumer is operating a 50 kilowatt induction motor at a lagging power factor of 0.8 with a source voltage of 230 volts RMS at 60 hertz. In order to avoid a penalty from the power supplier, the consumer would like to raise that power factor to at least 0.95. So maybe they have some kind of an arrangement with their supplier that they say, look, you have to keep your power factor at 0.95 or higher, or else we're going to hit you with some kind of a penalty. And they're trying not to have to pay that penalty. The way that some of these work is that you have to maintain that power factor at least all the time, right? So if at any point in time your power factor dips below whatever that threshold is, the power company might have the sort of right to ding you some kind of a penalty for having hit that power factor. Okay, that may not be the way it works for every place, but that's the way some of them work. So you're trying to make sure that your power factor doesn't dip below that 0.95 threshold. Okay, so here's what we got to find. What is the minimum value of capacitance that should be added to reach your power factor goal? That's question one. Question two is, how much capacitance can you add before you make it to where you start to have a leading power factor as opposed to a lagging power factor? The way that you would kind of infer that this is a lagging power factor is with this key word up here. It says you've got a 50 kilowatt induction motor, right? That probably indicates that that motor is inductive. And because it's inductive, it is going to have a lagging power factor, right? That means adding capacitors might help, okay? Or they probably will help. If you, if you had, for some reason, a leading power factor, adding capacitors isn't going to help, right? It's going to make it worse if you add capacitors when you started off with a leading power factor, all right? So that's just, I'll mention that. All right. And then the third question is the maximum value of capacitance allowable before your power factor goes back below that 0.95 threshold that you're trying to be within. In other words, it's possible to add more capacitance than you are supposed to and end up back in trouble with the power company, right? Because if you add too much capacitance, that'll basically take your power factor from a lagging one to a leading one, and it may go too far into the leading zone, right? So you want to try to make sure that you're not doing that. All right, where should we start? Okay, well, I tell you what I would like to actually start with here before I really do anything. I want to start by drawing what I call a power triangle, okay? And the first step of doing this, for this problem especially, is to identify what is the actual load, kind of the actual work-doing load that we are running with this induction motor, okay? And there's a clue in here that helps you know what that value is. I'm going to kind of represent that with a horizontal vector, right? And this vector is going to be in my imaginary and real space, right? So maybe it'll look something like this, where this is real and this up here is imaginary. So I'm going to start drawing some complex power stuff on here. So this is my P value. And what I was about to say is it gives you a clue as to what this needs to be because of the units that it gave you for this motor. You'll notice it did not say 50 kVA. It said 50 kilowatts. That's an important piece of information because when we use the unit of watts with respect to complex power, what we are talking about is the actual work doing part of what is delivered, right? So that means that the length of this vector right here is 50 kilowatts for that motor. All right, it also says that it has a lagging power factor of 0.8, okay? So what I'd like to show you here is kind of what that means. The apparent power that this motor is going to be absorbing can be represented with another vector, right, that comes up like this. We can call this length S, right? And the reason it does that is that the total apparent power that it is absorbing is the real portion of the power, the 50 kilowatts, plus the reactive power. And that reactive power that I'm showing right there is my Q value that is part of what I need to find out. So let me just label that Q. So here's a question I've got for you. Is there anything else that I can label on this little triangle based on knowing that it has a lagging power factor of 0.8? Let me give you a little bit more. One of the formulas that we had available for us to use was that apparent power, S, is equal to your real portion of your power, sometimes they call that active power, divided by your power factor. So what is that for us? This is going to be 50 kilowatts divided by 0.8, right? So 50 divided by 0.8, and that gives me 62.5. Okay? Now what units should I label this with? Okay? You might think it's kilowatts, but you have to keep in mind that we have some special rules about how we label these values, right? Because we have essentially 3 different ways to label them. We can label them with watts or multiples of those watts. You can label them as volt amperes, VA, or you can label them as VAR, right? VAR stands for volt amp reactive, okay? And the reason that we've got the 3 different kinds is that values that are measured along the real direction, we count those with watts. Values measured along the imaginary direction, we count those with VAR. And then ones that are a combination of the two, we count with VA. So when we do this right here, how should we label it? This would probably be kVA. So that means that I just came up with what the length was of this complex power vector, and it is just 62.5 kVA. That's not exactly what we needed in order to do our power factor correction just yet, but it might be handy. Why might it be handy? Okay, I'm going to show you why this might be handy. We know the Pythagorean theorem, right? So the Pythagorean theorem says that Q is going to have to be equal to the square root of S squared minus P squared, right? What does that look like for our problem? Okay, that'll just be the square root of 62.5 kVA squared minus 50 kilowatts squared, right? So let me put that in here. Square root of 62.5 squared minus 50 squared. That gives me 37.5. Now, how do I label this? What are my units for this? Okay. Someone says kVA. I would say kVAR. Why? Why should I label that kVAR? Okay. A good reason to label that kVAR is that that Q value is entirely in the imaginary direction, meaning that is power that is not really being delivered for doing something. It's power that gets delivered and then it gets sent back, and then it gets delivered again and it gets sent back over and over and over again at the frequency that the power comes in, right? So that's kind of, that's just what that means. All right, let me show you another way to do this, though, that I think is important to kind of link up, because there's 2 different ways that you can look at the geometry of this power triangle. The other one is to remember that it is going to be related to the power angle, right? You might remember that we had that the power angle was equal to the phase angle of the voltage minus the phase angle of the current there. But you might also remember that power factor, another way that we expressed power factor, was with the cosine of the power angle. Okay? In this case, we happen to know the power factor we're operating at, and so we can come up with a power angle, right? That will tell us how far off our, the two waves are, the current wave and the voltage wave. What's that phase difference between the current and the voltage wave? Okay, so here's what that would look like, right? Theta P is going to be equal to the inverse cosine of the power factor, right? So for this problem, that inverse cosine of the power factor is just going to be equal to the inverse cosine of 0.8. That gives me a 36.87 or so degree angle, and that angle is something that you see on this figure right here. This is our 36.87 degree angle. Okay? Well, once you know that angle, the other trig rules for this triangle still hold, and so that means that Q can be found by taking 50 kilowatts and multiplying by the tangent of that angle. So you'll see that this works this way too. 50 times the tangent, I believe that answer was the last one I had there. So that also gives me 37.5 kVAR. Okay, and I just wanted to show you sort of the two approaches you can take. They both work because all it is just a right triangle, right? So all the same rules that you have for being able to find lengths in a right triangle still hold for this. Okay, now it says, in order to avoid a penalty from the power supplier, the consumer would like to raise the power factor to at least 0.95. Okay, the angle kind of approach to that, kind of using angles down here, is what? You can say, well, the cosine, right, theta p, maybe I'll call it theta p target, is to basically say I want this to be the inverse cosine of 0.95 instead of what we actually had. So what is this value? Inverse cosine of 0.95, 18.1948 degrees. Okay. What I know is constant as I do this power factor correction is how much real power is being absorbed in the system, right? Because what I'm going to do is add a capacitor, and it's not going to absorb any real power, right? A capacitor won't do that. It doesn't have the capability of absorbing real power, at least not in large amounts. So what that means is that this kind of horizontal coordinate of where I'm going to hit this thing is going to stay the same, but what's going to happen is I'm going to reduce this apparent power to some new value. And that new value can be sort of thought of as having an angle here, right? Say this angle right there is 18.19 degrees or so. And what that gives me is what I'm trying to hit as far as my sort of acceptable amount of reactive power that I think I earlier called Q allowable. I'll abbreviate that Q sub ALL. So that's kind of my target value. I don't want it to be any higher than that for my reactive power. Okay? Well, how do I figure that number out? Okay, I can do that with my angle approach here by basically saying Q ALL is going to be equal to, you kind of use the same thing I did before, right? 50 kilowatts times the tangent of, this time, 18.19 degrees. So if I put that in here, 50 times the tangent, and I think that was the last thing I just calculated, so I can just say the tangent of that answer. It'll be 16.4342. Okay. What kind of units should I put on this one? kVAR again, because that is a value that is going to be measured entirely as an imaginary quantity. It's an entirely reactive amount of power. Well, now that I know that, I can figure out how much I need to reduce this reactive power to hit that goal, right? I need to reduce whatever my kind of original amount of reactive power was, and I call that Q sub C. And since these are both measured entirely along the same line, right? They're both measured in the imaginary direction right there. What that means is that I can figure out what that QC value is I can do that by taking Q overall, which was 37.5 kVAR, minus 16.4342 kVAR. By the way, I'm going to take that, I'm going to need that value, I know, for something later on, so I'm going to store that value of 16.4342 into a variable there. Anyway, I'm going to take 37.5 minus what I just stored in that variable. 21.066 kVAR. Okay. Now, what we're really doing here is we're taking this 50 kilowatt, slash 62.5 kilovolt ampere load, right? We're going to put this capacitor in parallel with that load so that they are both going to be doing a certain amount of power. And what we're doing, though, is we're reducing this amount of reactive power because it's going to go the opposite direction. It's going to be like a leading reactive power as opposed to the lagging reactive power that comes from the load itself. And so we can go into our formulas I gave you just a second ago that says that the reactance that we need, X sub C, has to be equal to the RMS voltage that we're driving all this with divided by the reactive power that we need to kind of add with our capacitor, right? And these are both values that we now know, right? Up here at the beginning, we said that we are driving this with 230 volts RMS, right? So this is just going to be equal to 230 volts RMS squared over Q sub C. And Q sub C we just figured out was 21.066 kVAR. All right. And this calculation that we're doing right here will result in units of ohms. Okay. So let's go ahead and do it. So we have, I'm going to store this into B. Now let's take 230 squared and divide that by what I just stored in B. But keep in mind what I just stored in B is going to be 1,000, right? Because I got the K there in front of it. So I'm going to take what I just stored in B actually and multiply it by 1,000. That way I get it into just VAR instead of kVAR. Okay, so 2.511 ohms. Okay, now sometimes people have a question right here and say, isn't that supposed to be J 2.511 ohms? Right? It's a good question, right? Okay. The answer is no, it's not J times 2.511 ohms because you might remember that our statement of complex impedance was that we had the resistance portion plus J times the reactance portion, right? So because of how we define the letter X when we're talking about impedance, the J is outside of that number, and so the X part of it is just a real number. Does that make sense? So just that, kind of head that question off before you ask it, perhaps. Okay? All right. That is the amount of reactance that I need. How do I figure out the capacitor value that I need to get that amount of reactance? Okay? Well, that's not too bad because all it is it's going to be based on minus J over omega C. Keep in mind that the J we're sort of eliminating from this because the J is outside of this X, right? So that basically tells you that the capacitance value that you need, which I will call C sub C, right? That's our corrective capacitor. This is going to be equal to 1 over omega X sub C. And so for us, this is going to be 1 over, what is omega for our system? 60 hertz, that is cycles per second, right? So this would be 60 cycles per second multiplied by 2 pi radians per cycle, okay, multiplied by that reactance value that we just found of 2.511 ohms. and let me get that stored also. Okay, so what this tells me here is that this should be 1 over 60 times 2 times pi times what I just stored in variable c. That was that amount of reactance. Now, what comes out of that calculation units-wise? Okay, think about what we're doing here. The cycle cancels the cycle there, right? Radians is not really a unit, and we basically have in the denominator ohms over seconds, right? So the reciprocal of ohms over seconds is seconds over ohms. And what is seconds per ohm? Seconds per ohm is a farad. So what we have with this is 1.0563. Originally it said times 10 to the minus 3. What's another way to do that same thing? The prefix milli is times 10 to the negative 3, right? So millifarads. So you need a 1.0563 millifarad capacitor in parallel with your load to get your power factor down to that 0.95 value. I should say up to that 0.95 value. All right. Questions about that? You ready for part B? Here's the good news. That was the hard part that we just did there. What do we need to do for part B? Part B says, what's the maximum value of capacitance allowable before the power factor goes from lagging to leading, right? What's another way to say that? What's your power factor right at the threshold for where it goes from lagging to leading? 1, right? And if your power factor is 1, then that means your S vector literally lays on top of your P vector, right? Does that kind of make sense? So how much QC do I need to cause my S vector to lay on top of my P vector? The entire 37.5 kVAR, it has to correct all of that back down to a power factor of 1, right? So that means I've already done the calculations that I need to. I need to reduce my reactive power component by 37.5 kVAR to get me to that state where I'm about to go from lagging to leading. Does that make sense? So what that would actually look like down here is that your QC is literally just the 37.5 kVAR, right? So for part B, all we have to do is say X sub C is going to be equal to 230 volts RMS squared over 37.5 kVAR, and this will give me this reactance value that I need. Okay, so 230 squared divided by 37.5, really what that's going to be is 37,500, right? Like this. That's going to give me a certain number of ohms, right? 1.411, we'll say, ohms. But why do I need that number? Okay, so that I can find C sub C, right, for this case. For this case, it's going to be 1 over, again, 60 hertz times 2 pi radians per cycle. Okay, now here I'm going to put in my 1.411 ohms. Okay, and I actually still have that as my answer there, so I'll just do it this way. 1 divided by 60 times 2 times pi times my answer. That gives me 1.88 times 10 to the minus 3 farads, or 1.88 millifarads. Now, here's a really good question. It's the part C of this same problem. What is the maximum value of capacitance you can have before the power factor goes back below 0.95? That's a problem again, right? Your power company doesn't like that either, to have a leading power factor. Okay, so you want to make sure you don't go that far. Let me show you what that means graphically, right? Because and tell you what, I'll copy this and edit it so that we get to kind of show you what this would mean to go kind of overshoot what you were trying to do. Here's what that would mean. This is part C. Okay. Now, what we're talking about is a correction that instead of going like this, it essentially has the same magnitude but goes too far, right? In other words, your allowable Q value is now going to be pointing down like this, right? That is kind of your allowable reactive power, right? And if you want to make sure you don't go any beyond that, then the maximum amount of reactive power change that you can have from what your original was is represented like that. Does that make sense? Now, we can do even more than that because we remember that a power factor of 0.95 led to an angle, right, for our new complex power vector that kind of comes down like this. We remember that that angle that we had there was 18 point, whatever it was, 119 degrees, right? That's the same, that power factor of 0.95 creates the same angle right there, and also means that this Q allowable quantity that I have right here is the same value as I had in part A. It's just flipped around and pointing the other direction. Okay, that's why I wanted to save that into one of my variables. So this value that I had up here of 16.4342 kVAR, I need to use that again, only this time it points down like this, and that tells me that QC is now equal to 37.5 kVAR plus, not minus, 16.4342 kVAR. Variable A. So I'm going to take 37.5 kVAR and subtract what I had stored in variable A. Excuse me, not subtract. I need to add what I have in variable A. That gives me 53.934 kVAR. What do I need for my capacitor? Let me show you something here. Some people like to collapse those two, I've been doing in 2 steps up there, into just 1 step, because all you're doing is you're finding an X sub C, then plugging that X sub C over here, right? Some people like to collapse that into 1 step, so 1 over 60 hertz times 2 pi radians per cycle, okay? And then I just take my calculation of what my XC value is that I need, and I plug that into the denominator down here. Okay, so that's just going to be equal to 230 volts RMS. That'll be squared, and we'll divide that by 53.934 kVAR. And that tells me that my required, or that my capacitor value, that if I go above this capacitor value, it causes me to go back below my acceptable power factor on this. I can calculate that with this number. So 1 over 60 times 2 times pi times 230 squared divided by, I believe this 53.934 was already stored as my last answer, but I need to take that and turn it into just VAR, not kVAR, so I'm going to multiply it by 1,000. Now that gives me a capacitor value that I need of 2.704 millifarads. So a way to interpret that is you want to make sure that when you are trying to do this power factor correction, you don't want to plug in a capacitor that has more than 2.704 millifarads in, or else you are going to be back in trouble with the power company. Okay? Questions? All right, now do you want to see this in action on your breadboard? Of course you do.